The next talk from Masahito Yamazaki and Generalized Chiral Potts model and Hyperbolic Monopoles from Chern-Simons theories.
Great. Thank you so much for the introduction. And it's really an honor for me to speak at this event, celebrating the life and achievements of Professor Rodney J. Baxter. So for me, Rodney's work has been really our source for inspirations. And to some extent, I made a significant portion of my career trying to understand what he has achieved in my own language. And for the most part, I was learning from his papers and his books. But more recently, I had the pleasure of meeting with him in person. So this is the photograph from one of the events, Baxter events in 2021, I guess, and we see Mari and Barry and Rodney and his wife, and it was really a remarkable experience for me, and we will miss him forever. So today I'm going to talk, of course, about integrable models, and this equation appeared many times, and it's a really remarkable that such a simple equation has such a far-reaching consequences in all different branches of physics and mathematics, and really inspired decades of work in various different communities. And of course, this equation was solved by Baxter in his study of the 8-vertex model. And in 1971, almost 50, I think more than 50 years ago, and this paper still contains many of the remarkable results. He even has a Q operator, I remember, and he also has a remarkable mastery of the elliptic functions, which was crucial for this work. And to some extent, this elliptic solution is still one of the state of the art in the discussion of the Yang-Baxter equation. And what I mean by that is that people try to go beyond. First of all, people try to understand the 8-vertex model. And in fact, this is a very non-trivial result. For example, Richard Feynman, the famous physicist, tried to understand the 8-vertex model on his own way. But after some trial, he failed. So it's a very non-trivial achievement, especially 50 years ago. And one of the questions which I'm sure occurred to many people in the history is that Baxter was able to solve the Yang-Baxter equation using the elliptic function, which is the function which lives on the elliptic curve, which is genus 1 curve. So it's very natural to imagine that you can try to go to higher genus. And there is some concept of theta function associated with the higher genus theta functions. So you might naively think that, okay, so Baxter solved it for genus 1. So why don't you go to higher genus and then try to find new solution of the Yang-Baxter equation? And it turns out this approach is surprisingly extremely difficult. So there are a lot of reasons, but at least one of the basic reasons is that it's not easy to come up with some, to preserve some properties. For example, in most of the discussion of the Yang-Baxter equation, the R matrix is a function of spectral parameter, Zi and Zj, but it only depends. It depends only on the difference. So this is known as a rapidity difference property. And but however, if you go to higher genus Riemann circuits and you take 2 points, there is no natural concept of the difference of 2 points on the higher genus curve. So you cannot write down this equation if you go to higher genus Riemann surface, and you have to throw away this condition. So that's one of the subtleties associated with going to higher genus. And in fact, this rapidity difference property is reasonably strong. So you can impose extra conditions. For example, you can impose this quasi-classicality. So impose the condition there is H bar, and starting with the identity operator. And then there is a nice classification by Berabi and Riefeld. With some extra assumptions, they could prove that all the solutions to the R matrices are either rational, trigonometric, or elliptic. And of course, the elliptic case was the case discussed by Rodney Baxter. So it turns out that it's actually very difficult to go beyond what Baxter has achieved already. Now, So this was the state of the art. To some extent, it still is. But interestingly, it was Baxter himself who was successful in going beyond this elliptic barrier. And that was the achievement of the Chiral Potts model. So this is one of the foundational papers on the subject of the Chiral Potts, going back to 1988, with Rodney and Jack Park and Helen Yang. And there also related paper by Helen and Barry and Jack and his students. So there are many people contributing to the subject, but Baxter was also playing a significant role in this development. And this solution, which I'm going to call as a Chiral Potts model, is a rather remarkable solution, and it's still one of the state of the art in the integrable models. And compared with many other integrable models, which people are familiar with, this has a very peculiar property. Well, first, there is no rapidity difference property, as I emphasized before. It has no nice quasi-classical limit, which starts with the identity. And of course, the genus is greater than 1. Now, how does the spectral curve look like? And it takes a very, very peculiar form. So this is the equation. So it's an equation for ABCD, 4 complex coordinates. And you regard it as a coordinate by modeling out the overall multiplication as a coordinate for CP3. And there are a lot of 4 equations, but actually there is a redundancy, and this defines a curve. And there is some parameter of the curve, which is k and k prime. But you can fix this k and k prime to some particular values. And you can compute the genus, and genus is n squared, n minus 2 plus 1, where capital N is the number of components of the spin. So it's a Zn spin. So this is the Chiral Potts model spectral curve, and it was mysterious, and it still is extremely mysterious from where this curve comes from. So it's a very mysterious curve. And so what I'm going to talk about is to try to shed light on this Chiral Potts curve from a slightly different angle. And in fact, so this curve itself is a very peculiar curve. So and in fact, so when n is 2, this curve is genus is 1, which is elliptic, and when you go to n equals 3, so genus is already 10. So and it seems crazy to talk about the genus 10 curve. So when Jack Park was interested in that, some string theorists are interested in genus 2, and then they were not, well, it looks like a crazy thing to talk about genus 10. So it was mysterious, and it still is. But at least the nice thing, first of all, the nice thing is that it becomes at least a part of a larger structure. So that is the story I have been working on for some time. So you can start with some quiver gauge theory, so-called, and then construct the model. So one of the models is the model which we constructed with Andrew Kells, and then you can take a various reduction procedure. And the Chiral Potts model is a part of this larger family. And there is a nice limit, semi-classical limit, which Vladimir and Sergey and others discussed. And then that's where the Chiral Potts model comes from. So at least it's a part of a larger family. It's not a completely isolated one. So we have a slightly better view, understanding of the Chiral Potts model, but I would still say that it's still mysterious. And in this talk today, I'm going to revisit yet another connection with a completely different topic, which is the connection with hyperbolic monopoles. And the observation goes back to the paper by 1991 by Malka Atiyah, entitled Magnetic Monopoles and the Yang-Baxter Equations. So in this paper, he compared the Chiral Potts model of the spectral curve, which, as I described, is a curve of higher genus, with the so-called spectral curve of the magnetic monopole. And it turns out that he found some connection. So there is a quotient procedure, which I'm going to describe, but in the end, he observed that the two curves are the same. And that raises a lot of questions. Maybe there is a more direct correspondence, or maybe one can incorporate the insight on the one side to learn about the other side. and so on. So what did he observe? Well, first of all, we start with the Chiral Potts curve, which is the same, I copied from here, sorry. So this is a curve, and in the CP3. Now, what Atiyah did is to take a quotient by Zn. So you take some quotient, omega is the nth root of unity, and it's a free action, and then define the quotient to be sigma n. Now, this is a curve inside the P3 divided by quotient, but now that we take a quotient, you can actually regard the sigma as a curve inside the C star quotient of P3. You have to take out the two P1s, but roughly P3, this was the original ambient space, and you divide by the C star action. And then you get the P1 times P1, two copies of P1. So the curve, after the Zn reduction, the curve is inside the P1 times P1. So that's a simple fact, no mystery whatsoever. But you get a curve inside P1 times P1. Now, on the other side of the correspondence, we actually have another curve inside P1 times P1. Now, the other side of the correspondence, we study the monopoles in hyperbolic space, H3. In the discussion of monopoles, there is a so-called twistor correspondence going back to the work by Roger Penrose. And what they say is that if you want to study the monopoles on H3, the hyperbolic space, you should go to the twistor space. Or in this case, more precisely, the so-called mini twistor space. And you should consider holomorphic bundles on the mini twistor space. And it turns out that for H3, Hitchin observed, actually for Hitchin observed originally for R3, and then people generalize it to H3. But for this H3 case, it turns out that the twistor space in question is a P1 times P1. It's called a mini twistor space. And in that discussion, so the geometrical meaning of this mini twistor space is that in H3 you consider geodesic, and the geodesic has two endpoints, which takes values in the boundary of H3, which is P1 times P1. And this is and then there are two boundaries, and then that's the point. You specify 2 points on P1 times P1, which is this P1 times P1. So you obtain some spectral curve inside P1 times P1. And now the statement of Atiyah, and also later by Atiyah and Murray, is that these two spectral curves, both inside P1 times P1, are essentially the same. So this is the Atiyah's observation. And interestingly, after more than 30 years of Atiyah's observation, very few papers, essentially close to zero paper, appeared on the subject. Atiyah's observation was interesting, but it looks like a curious observation, and the meaning was completely unclear. So what I did, and what I'm going to discuss for the rest of my talk, is to try to understand this better. And there are two ingredients. The first is to generalize the correspondence to the case of SUN gauge groups, SUN hyperbolic monopoles. And the second is to try to come up with a conceptual framework for understanding it. It may be a curiosity, it just might be a coincidence, but if there is a physical setup which explains this structure, then we might be able to extract more. And I should say that I don't have a complete solution to the question number 2, but at least I have now a very good narrative incorporating many of the structures discussed already. So let's first go to this generalization to the AN case. Well, so fortunately, there is already a generalization of the Chiral Potts model discussed by Bajanov, Kashayev, Vangazev, and Stroganov. Sorry, there was an A missing here. So sorry about the typo. But let's see. So there is an A1. So in the A1 case, which is the original Chiral Potts model, you have Zn spin, where there is a number of component spins, capital N. And then there is an AN generalization, where there is a small n, which contains copies of this Z large N spins. So small n minus 1 copies of the Z large N spins. And they constructed the remarkable model whose spectral curve has a genus of this formula. So it grows even faster than the A1 case. Now let's try to imitate what Atiyah did. So the spectral curve takes values now, instead of P3, P of 2 small n minus 1, with the 2n coordinates. And inside these 2n coordinates, you impose this condition, where you take a pair of I and j, and then so there is z plus z minus of the I is related to z plus z minus of the j, with some coefficient kij, which satisfies some consistency conditions. So this is the spectral curve they found. And if you want to imitate what Atiyah did, you should first take a quotient, z large n to the power small n minus 1. So previously 1 copies of zn, but now we take multiple copies of zn, and we obtain, we take a quotient somewhat similarly by multiplying each zi plus zi minus by some root of unity. So this is and again, this is a free action, and it defines some curve. And the point is that so original curve was defined in p 2 small n minus 1 with the 2n coordinates, but you can gather together 2n coordinates to n copies of 2 coordinates. Each of the 2 coordinates defines a pair p1. So you get a copy of p1s, and the original curve, once projected to the I and I plus 1 component, defines a curve inside 2 copies of p1. P1 i's p1 and I plus 1's p1, and there is a curve sitting inside it, which I defined si. So the original spectral curve was a complicated one, but I kind of decomposed that into something simpler. And in the end, you get a curve which is inside p1 times p1, which was the curve, which was very similar to the situation for the A1 case. But we just have a copy of such ingredients. And it turns out that this matches nicely, this structures match nicely with those found in the discussions of hyperbolic monopoles. So in the case of hyperbolic monopole, there is SU small n, and in the typical discussion of SU small n, there is a Dinkin diagrams and things like that. So SUn small n has n minus 1 simple roots, each of which behaves like a A1. And indeed, each such a simple root corresponds to a curve inside P1 and P1, and it satisfies some conditions. They intersect transversely and then has some certain number of intersection points and things like that. And this data, geometrical data, is precisely the data for the hyperbolic monopoles, which were discussed by Atiyah and also by Murray and Singer. So this way, by keeping track of this, we have succeeded in generalizing the correspondence of Atiyah and also Atiyah-Murray to the SUN case. Of course, this raises a question, like why does such a correspondence hold? So since we want to relate generalized Chiral Potts model with the hyperbolic monopole, the natural idea is to try to embed both of these ingredients in something larger, such that each of these ingredients are contained. And in fact, this type of discussion is familiar in the discussion of string theory. String theory has a lot of dimensions, 10 dimensions and things like that. So many of the ingredients can be embedded there. And if you project into some different directions, you get completely different looking aspects. And it turns out that story works. So in our discussion, what we have is the 6-dimensional Chern-Simons theory. Well, in the paper, we also discussed the 10-dimensional Chern-Simons theory. But let's start with the 6-dimensional Chern-Simons theory here. And you can keep reducing. And then you get both these aspects. So that's what I'm going to discuss for the rest of my talk. Now, first, we start with the hyperbolic monopole. So it's an equation F equals star d phi on H3. And it turns out you can obtain this from more familiar equation, which is the 4-dimensional Self-Dewar-Yang-Mills equation on R4. And the reason is that R4, if you remove the R2, is conformally equivalent to H3 times S1. So I wrote down the simple manipulation here. Oh, sorry. Let's see. I need to go back. Yes. So because there's up to this removal of R2, R4 is conformally equivalent to H3 times S1. So and then you can reduce along S1 to go to H3. So 3D hyperbolic monopole can be obtained from 4-dimensional anti-Self-Dewar-Yang-Mills equation, 4-dimensional instantones. And in this discussion, you can also invoke the twistor theory. In the 4-dimension, the twistor theory, or the original twister for the pen loads is P3. But down in 3 dimensions, you have to take a quotient. And that's the mini twister, which I introduced before, which is roughly P3 divided by C star. Now, the fact that there is a twisted correspondence means that everything can be recast as a holomorphic bundle. And the holomorphic bundle in physics language arises from Chern-Simons theory. So here you start with the 6-dimensional holomorphic Chern-Simons theory of P3, which is the original twisted space for 4 dimensions. And again, if you remove some P1, which is the point at infinity, then this is the same as R4 times P1. And if you remove reduce along this P1, you get the anti-Yamazaki equation R4, which in turn can be reduced to 3 hyperbolic monopole, as I explained before. And this structure explained nicely. So there is an extra P1 direction, and that this parameter, we play the role of the parameter when we write down the Lux equation of the 4-dimensional Yamazaki equation. Now, so I explained this right-hand side of this story. So you start with the 6-dimensional holomorphic Chern-Simons theory, reduced to 4-dimensional anti-Yamazaki equation, 4-dimensional instanton to hyperbolic monopole. Now, once you come to the 6-dimensional theory, you can also try to reduce to a different direction. For example, in the 6-dimensional holomorphic Chern-Simons theory, you have R4 times P1. But this R4 you can compactify to R2 times T2 and then reduce along the T2 direction. And then what you get is some 4-dimensional theory. So some of the holomorphicity is lost, and it turns out you get the 4-dimensional Chern-Simons theory, which is holomorphic in some directions and topological in some directions. Now this R4 is replaced by R2, so you get a theory of R2 times P1. So you get a 4-dimensional theory, Chern-Simons-like theory on R2 times P1. And this is exactly the theory which we use. B means myself and Kevin Costello and Witten used in order to explain integrable models. And I believe Edward gave a talk about this earlier this week. So this is a 4-dimensional theory defined to R2 times P1, and with the coordinate Z, and then there is a ZZ, which the holomorphic Chern-Simons term. And what we did a couple of years ago is that starting with this Chern-Simons theory, and then do the perturbative quantization, you can explain many different aspects of integrable models. For example, classifications, or the R matrices, and the representations of Youngian, etc. And I'm not going to give any detailed explanation of that, but at least one idea, one very basic idea is that there is so this is the 4-dimensional theory R2 times P1, and there are some lines, so-called Wilson lines, but the theory is actually topological in this direction. So you can move these lines around, and that gives the Yamazaki equation. So basically the story is there. Once you have this 4-dimensional Chern-Simons theory, you can try to connect it to integrable models, and you might conclude that that's the end of the story. So you have a 60 holomorphic Chern-Simons theory. You get the 4-dimensional topological holomorphic Chern-Simons theory, and then go to the Chiral Potts model. So that's going to be the strategy. Well, except that there is something strange about it, because the model we get is R2 times P1, and P1 plays the role of the spectral parameter. So if you just naively believe in this, we seem to have P1 as a spectral curve. But of course, if the spectral parameter takes values on P1, it means that the model is rational. But of course, Chiral Potts model is not rational. It has higher genus Riemann surfaces as the spectral parameter. So this looks like a contradiction, but actually there is a way out, which is that what we should get is actually not just the P1, but P1 with a lot of singularities and defects and branch cuts, they're all. And this is related to some of the subtleties, which I didn't emphasize too much here. So for example, when we relate P3 to R4 times P1, I have to take out the P1, which corresponds to infinity in the twisted space. So you have to pick up something, or when you reduce the 4D to 3D, the hyperbolic monopole, you have to take out R2 in terms of R4. So these look like singular defects inside it. In fact, up in 6 dimensions, holomorphic Chern-Simons defined in Calabi-Yau, but P3 is not Calabi-Yau. But the trick is to take out some P1 so that the rest is well defined. So it's not just P3, but P3 with a defect. So if you go down all the way to P1, we expect the P1 with some extra structure. And now our proposal is that so such a branch cuts, we could write to a branch cover. So the Chiral Potts model, spectral curve of the Chiral Potts model, or actually the Zn quotient thereof, which I denoted the sigma before, can be written as a branch cover, n-fold branch cover over P1, which is a very specific holomorphic one form, which I denoted as here. And then so that is the proposal. So the proposal is that you start with the P1, but with branch cuts, so that the rapidity difference property is lost, and then whose pullback gives rise to the Chiral Potts spectral curve. And this setup we will realize the Chiral Potts model. Now, not everything is worked out, but this sounds like a plausible story. So in the end, we can now close the circle. So we start with 60 holomorphic Chern-Simons go to 40 Chern-Simons on Chiral Potts spectral curve, which is an n-fold cover of P1. And then since we get the Chiral Potts model, that it gives a conceptual explanation of why there is any connection to the 3D hyperbolic monopole. So let me summarize my talk. So I started this discussion by 8-vertex model solution of the Yang-Baxter equation, which is still a remarkable solution, the elliptic solution. And I also discussed in what sense the elliptic solutions do the end of the story under some assumptions. For example, the spectral parameter rapidity difference property. But of course, these are rely on some assumptions. You can try to remove these assumptions and then explore different types of solutions. And then very few solutions are known, but the Chiral Potts model, which Baxter was partly involved in its discovery, was one of the state of the art. Now, what I discussed today is to try to connect it to some completely different ingredient, hyperbolic monopole, and build on this relation or original observation by Atiyah and Murray. I extended the correspondence. And second, I tried to put that perspective by starting with the 6-dimensional holomorphic Chern-Simons theory, which seems to give a natural explanation of the relation between the two. Thank you.
Thank you very much. Any questions? So I do have a question.
Okay.
Which I asked Professor Witten. Is there a relation to 3-dimensional lattice model?
Like a tetrahedron equation.
Yes.
Yes, I think that's a very interesting question, and I don't have a definite answer yet. In fact, that's the question which has been raised many times before. So one natural idea is to try to consider Chern-Simons theory in a different dimension, and so that instead of so in the typical discussion lattice model, we have lines in the Yang-Baxter equation, which is a one-dimensional object, and that's one is related to the fact that we have a one-dimensional gauge field. For example, now you can try to discuss the sum theory in higher dimensions, where the gauge invariant observable is associated with a surface, a string, which is a two-form gauge field, for example, and then you try to repeat the story. And some of that story, and most naively on the first pass, it seems to work straightforwardly by moving things around, etc. But of course, the question is to reproduce the precise structure of the tetrahedron equation. So as you know very well, so it's very more non-trivial to construct the solution of tetrahedron equations. So I think I would say, so the short answer is that I would say that it's relatively easy to try to imagine that similar correspondence. You can generalize this to describe the tetrahedron equation. But to try to match the exact structure people have found and precise difficulty for the tetrahedron equation, that's work to be done, I think.
Thank you very much. So let's thank the speaker again.